Yeah, thank you. Thank you, Pim, for and all the organizers for the invitation. It's a pleasure to be here. And please feel free to interrupt me at any time if there's something that is unclear or whatever. So I'll try to start with what Nico said. And maybe I will repeat myself, but not for more than 5 minutes. So don't worry too much. But it's also good for you, if you're not familiar with the topic, to just have a clear idea of what's the goal in this problem. No? So what I'm going to talk about is like the same problem that Nikos did, but what happens when the degrees are very large? But when the degrees are very large, it turns out that there's first of all, there's some problems coming from this fact that the most useful tool in the sparse case, which is this configuration model, is no longer working. And also like there's some new phenomena appearing, which I think they are very interesting. And this is something that is quite different from percolation in general. So hopefully I'll manage to interest you in the topic. And if you are interested, yeah, there's plenty of open questions still left. So I invite you to think about them and yeah. It's a nice problem. So let me just say that what I'm going to be talking today is joint work with Guillem, who's currently a postdoc at ISTA in Austria, and also with Dieter Mitsche, who's in Chile at the moment. So let me start, with, I'm not going to be using, there's a lot of notation that is similar, but not all of it. So I'll try to stress with something different. So G is just a graph. L1 of G is just the order of the largest connected component of G. And this is essentially what we want to understand, like how large is the largest component. And my P is just going to be a probability. And as Nico said, like this is something that might depend on N. So it might go to zero when N goes to infinity. And we do we consider random graph, that we call the bond percolated graph of G, which we keep the same vertex set. You can think about the vertex set being just the first n integers if you want. I mean, it's perfectly fine. And then each edge in G is present in GP independently with probability P. So it's just like we take a random sample of the edges of G, and we consider the subgraph that is induced by them. So, so this is the general problem. So what are we going to talk about today is this D will stand for my degree sequence. So this was the calligraphic D of Nikos, but I'll use this bold D. And I will drop the dependence on N just to make it easier, but you just have to think that this is always a degree sequence of length N. And G and D is just a set of simple graphs on these vertices 1 to N with degree sequence D. And what I'm going to do is I'm going to choose one graph from this set uniformly at random. And I will denote it by G and D, or if it's clear from the context, I will just say G. So our object of interest is this percolated random graph with a given degree sequence, which is you have like your, just a second. Okay. Can you see this? You can see it, right? Yeah. So it's like you have your graph, and then you percolate this graph, and you can obtain GP. Something that is interesting is to know that there's two levels of randomness here, right? So there's a first level of randomness where you choose this random graph. And then there's a second level of randomness, like once this random graph has been fixed, then for every edge of this graph, you percolate with probability P. So this is kind of a double random process. Okay, so what's the question we would like to answer? What's our goal? The goal is to understand what's the component structure of GP in terms of P. So P will go from 0 to 1. So what's going on with the component structure? And then there's this phenomenon that we know as percolation, and Nikos already talked about this, which is this point that we call PC, where before PC, GP is is fragmented into many small components. So there's no clear big component appearing. And after PC, suddenly GP has similar component structure as G. So suddenly, for example, if G was connected or had like a huge component, then GP also has a huge component. So this is known as the critical probability for percolation. And here I just put a list of models. Some of these models were also introduced by Nikos. For example, I know you could think about grids. You can think about like these are different sorts of grids. You can think about hypercubes. Here, my n is really the number of vertices. This is where you see 1 over log n instead of 1 over n. You can think about expanders. You can think about products of graphs. And in particular, if you percolate the complete graph, then what you obtain is this binomial random graph, or that it sometimes is also called the Erdős-Rényi random graph. And it is well known that this random graph has like the percolation probability is 1/n. So going to these random graph models, the one with a given degree sequence, also what Nikos introduced is like this result that was independently proved by him and by Svante Jansson, that says that under suitable conditions on the degree sequence, so he gave more details about which sort of conditions you need, but for example, finite second moment, then if you look at this expression here, which is the one, well, it's the one that we saw before, right? This is the critical percolation probability. And the way to prove this is using this so-called configuration model. And yeah, Nikos already said something about the configuration model, but the idea is that the configuration model allows you to study random graph with given degree sequences as long as your degree sequence is sparse. At the moment that this degree sequence is not sparse, then it fails. And then I'll say something about why it fails. And as we saw in the previous talk, also like Bolobas, Riordan, and Nikos, Felix, and myself, we also worked on this. Well, we kind of went further with like trying to remove some of these conditions on the degree sequence to have like a nice description on the sparse case. Okay, so what can we say in the dense case? So as I said, like for me, sparse case means that M, which is the sum of the degrees is just twice the number of edges, so M is bounded in terms of N. So it's just linear in N. So this is what we have discussed so far. And now I'm going to be talking about the so-called dense case. So the dense case is just when M divided by N goes to infinity. So when there's many more, like when your average degree goes to infinity, you can also think about this. When there's much more edges than vertices. Then suddenly, like if you think about this, say, well, I mean, suddenly, like if you really have like many edges, probably you have to delete also a lot of vertices, a lot of like your probability P should be very small, right? Because otherwise you won't be able to disconnect anything. So this case so far is not very well understood, also not very well studied. And there's kind of two things, and this is what I was saying before, there's kind of two things that one should take into account. The first one is that the methods that have been used so far are not going to be very useful here. And the problem is that it's about this configuration model thing. So the configuration model is not a model of simple random graph, but a model of multigraphs. And this multigraph turned out to be simple quite often if your degree distribution is nice, is sparse in some sense. So as long as your degree distribution doesn't have too many high degree vertices, then this probability of being simple that you see here is going to be, say, a constant. So if you prove some result that holds with high probability in this model of configuration model, then you will be able to transfer it to simple random graph. So this is what I mean by this transfer theorem. So transfer theorem just tells you that if you prove something with high probability in one model, then it's also true in the other model. But this probability here, if now you allow your degrees to grow, it turns out that this probability decays exponentially fast in terms of something that is, well, I'm not going to say it here, but I mean, just something that depends on the squares of your degree sequence. So then suddenly you have that the probability that this is simple goes to zero very fast. And then if you want to use some sort of transfer theorem, you are in a problem. I mean, it's still theoretically possible to do it. And there's some people that do it, but it's going to be much harder. And at some point, it will break. It will really have no at some point. So this is the first kind of problem. We need to find new methods, and this is why we use this sort of switching method that I'll talk about this later. And the second thing that is also different is the nature of the phenomenon. And what I mean by this, and now I'll give some examples. It's that this kind of paradigm that we were introducing about this existence of a single critical point that changes the qualitative behavior of the component structure, this thing in general is no longer true. So I will give you some examples where this thing kind of falls apart. And this is what I think is nice from this topic, that suddenly it's something very different from what we have seen so far. So as I said, like it's not very well understood, but we still know some things. with about this graph, about this dense random graph. So something, for example, that we know how to do pretty well is how to count them, how to sample them. So there are many results like, I know, McKay, Greenhill, Wormel, like many different authors, especially from Australia, that devoted like many papers about how many of these graphs there are, how to sample them. And then there's also like, we care more about this component structure. So there's this paper of Jos, Rautenbach, Reed, and myself that also Nikos talk about. That is about giving like a full criterion, like a criterion that applies to all degree sequences for the existence of a giant component. Let me just say that in this case, if you're not percolating, right? If you're not percolating and you have a dense degree sequence, then this makes your life much easier in some sense because you have a lot of edges. So of course, if you have a lot of edges, it will be easier to check that there's a giant component, right? Because it makes sense. Lots of edges will create a giant component. So this is not going to be the case here because if we have here more edges, then just a second, if we have more edges, then we're also going to percolate with a small probability. So at the end, the number of edges will be also still like very few. So in this case, it's a bit more challenging than in the case where percolation. Okay, so what else? Let me talk about a couple of particular cases. So also I'm here, I'm repeating myself a bit from Nico's talk, but let's just assume now that we have a regular degree distribution. So meaning that I fix some D, like the D that I want. I mean, it could depend on N. It could be at least 3. And then I take what is called a random regular graph, random D-regular graph. So among all the D-regular graphs that I may have, I choose one uniformly at random. And then I can think about percolation. And as Nico said, Gerd and Alan, Benjamin, and Stacy studied this, and in particular, they proved that the threshold for percolation is 1 over D minus 1. So Gerd proved it directly in this random graph. Alan, Benjamin, and Stacy, they were studying expanders more in general, like with expanders of large girth. But this is for constant values of D. And remember, we are not interested in constant D in constant degrees, but we are interested in degrees going to infinity. So what happens if you take any possible degree? And then these papers were not really studying this, but it's a consequence of their results. So in this first paper, Krivellevich, Sudakov, Bu, and Wormel, what they prove is that this G and D is an expander. It behaves like an expander for all D. And Krivellevich and Sudakov, what they prove is that if you do percolation in this particular sort of expanders, with D going to, then that your percolation threshold is 1 over D minus 1. Here, the minus 1 is not really important because, well, I mean, it's important if D is constant. If D goes to infinity, it's not so important. But what is nice about this result is that somehow it gives you some sort of interpolation between, say, cubic random graph, which is something kind of very well structured, D equals 3, and the Erdős-Rényi model, right? Erdős-Rényi model is like you're percolating a random regular graph of degree n minus 1. With the graph, but in particular, you're taking this as a random graph and then you're percolating it, right? So in some sense, you can see this result really as interpolation between these two points. Okay, so then Benjamini asked, what about the critical window? And Nachmias and Perez and Jos and myself, we studied this problem and we saw that in fact, the critical window at the percolation threshold behave like the one of the Erdős-Rényi random graph. So Nachmias and Perez prove it for constant D and we prove it for D going to infinity. So somehow the message of this slide is that for the regular case, there's no qualitative difference between percolation in random regular graphs. So it really behaves like the same. The location of the threshold is the same. The critical window is the same. It's really like you have this sort of parallelism between, of course, maybe the constants are going to be different, but you have this sort of parallelism between two things. Okay, let's go a bit further. And then we also have this paper of Bolovas and Riordan that also study percolation in the sparse case, but they also have some comments about the dense case. And here I just copied a piece of their paper, which is the following. So as soon as we, it makes very good to allow the average degree to go to infinity and study the percolated random graph. All we shall say here is that in many situations, for some appropriate p, the degree sequence, which is random now that you obtain, will with high probability be such that this theorem 1 applies to it. Okay, so just now here you have to believe me, this theorem 1 is just some sort of percolation result that has kind of qualitative similarities with the Erdős-Rényi random model. So what they were saying is like, well, I mean, we don't know what happens in every case, but there's like many situations where what we have done, which is this sparse case, you can somehow translate this thing to the sparse case, and then it will behave like in the sparse case. In the sparse case, you always have this sort of percolation, critical percolation, and Erdős-Rényi-like behavior around this threshold. So, for example, an example of this sort of sequence is suppose that all the degrees in your graph are comparable in the sense that they are all of the same order. Say, I don't know, they are square root of n times some constant. So then this would be the case. But there are different things that can happen, and this can go wrong. So what are the kind of two questions that we're interested in? So the first question we're going to be solve this. It's true. And D behavior as a percolated complete graph, which is this GNP, right? What do I mean by the same behavior? I mean, is it located always at the same place? Is it a critical window also around it? What's the width of the critical window? Uniqueness and size of giant component? All these sort of questions we were all interested in. So if this question is false, meaning that it's not the same behavior, then we would like to understand under which circumstances, or what can be said otherwise. In general, like, give me like some tools, give me tools so I can tell you something about your largest component. Let me start with answering this question 1 in the negative sense. So it's not always true that the phenomenon that you will see in this dense random graph when you percolate is similar to GMP. And the thing here is like, while in all the models that we have seen, there's this like unique PC, such that before PC you are poorly connected, where you have like very, very small components, and after PC suddenly something emerges and you have a giant component. This is no longer true in this dense random graph. So I'll give you 2 examples. The first example is here I just put exactly one degree sequence that looks like this. So I take half of the vertices of square root of n, a fourth of the vertices of degree n to the 3/4, an eighth of the vertices of degree 7/8, and so forth. And then it's not too hard to prove the following. Say that you take P alpha, this is a probability, alpha is, I take P alpha to be n to the alpha minus 1. And you take this C alpha that looks like this. This is the plot of the C alpha. So C alpha is more or less like alpha, but you have this ceiling thing, right? That makes that your function keeps jumping. So it jumps around the x equal y line, around like this, right? So this x equal y, but it goes like this and it jumps. It goes, it jumps, it goes, it jumps. So what you can prove, and it's not complex. Of this percolated graph, this here is the value of the exponent. So somehow parameterizing in a maybe a different way than what we are used to. But then the largest component is of order C alpha times n. So what does it mean? It means that there's infinitely many places where this component like jumps in a very small, like in a small window. So for example here, so in fact, it has infinitely many jumps. So it goes like this, it jumps, it jumps, it jumps, it jumps. So it keeps growing. So it's not like in the previous case where you only had like a single jump that was going from something small to something already linear. But here it jumps and it's linear all the time. So you really have like a giant component all the time. But the constant in front of the giant component is not continuous. So it's just, you have these jumps. So it turns out that this was before, and reordering marker, for example, showed something similar in the context of actually OWPS processes. So let me say, like a second example. So, okay, can you hear me well? Because Pim was sent like a message that there were some problems.
Yeah, it sometimes stutters a bit, but overall, I think I can follow quite okay.
Okay. Just let me know if there's any problem, and I'll try to do something different. Okay, so let me give you a second example, which is still, in my opinion, is still like more surprising. Is the following. So you can find some degree sequences such that like you choose your k. K is going to be the number of jumps. Choose your k, and then there exists some delta positive such that there's like, now here have also increasing sequences, alpha I and beta I, such that around these points, around p being n to the alpha I minus 1, so if you take p to be slightly smaller than this, your largest component is going to be of order n to the beta I minus delta. And then if you take p to be slightly larger than this, then your largest component will be of size at least n to the beta I. So here, like, again, in a narrow interval, like this is like a small interval, right? What you see is the jump of your component size, but not only one, but many, right? There's k of them. So the beta i's are increasing. So you grow your components, and you do this like not continuously, but really like you jump. So let me do a drawing of how this thing looks like. So the graph looks a bit like this. So sometimes you call it the onion. And so you're gonna have like a inner core. Well, I mean, so far here it's like p equal to 0, so there's no edges. So, but there's like a small number of vertices that have very high degree, and then a slightly larger number of vertices that have a slightly smaller degree, and then more vertices that have less degree, and so far, and finally you have most of the vertices have very low degree, right? And you do it in such a way that while the number of vertices here is growing, the number of edges is decreasing. So most of the edges are inside here, and then inside here, and then inside here, and so forth. So what's going to happen when you percolate? So what you have is the following. So you start percolating, and then you percolate with very small probability. So because most of the edges are inside the red thing, you're only going to see edges essentially inside the red thing, maybe between the red and something else, and then increase your probability. And then this thing keeps connecting, right? And you see how this thing is growing. So initially, like your giant component is only going to be inside this red thing. After some probability, it will reach the orange part, and then you will increase your probability, and it will reach the yellow part. And the way how it invades each color, there's a threshold for this, right? So there's really like a threshold for like expanding in a color, and this is what forms these multi jumps, like infinite, like as many jumps as you want. So you keep growing, and at the end you have some graph that looks like this. Maybe it doesn't look very nice, but it's something like this. So hopefully it's clear what thing is going on, right? So it is quite different from what we are used to. And so yeah, as I said, like there's these two examples, and somehow these two examples motivated a bit the results I'm going to give you now. And so let me just say what can we say and how this is useful. So I'm going to give you a number of results. Hopefully it will be clear on where we use each one. And also let me say that even if I give you a number of results, we are still far from having a complete understanding of what's going on. So we know like these results are going to give us some tools for in some situations be able to detect a threshold here, like that goes from this to this, but still like we don't have like a full description. Like we would like what we would like is to like you give me any degree sequence and I tell you exactly how many thresholds do you have and what's the size before and after each of the thresholds and so forth. And this thing is still not, I think we're still far from having something like this. So there's a lot of room to work on these sort of topics. So I'm going to talk about these three topics very briefly. So first, I'm going to give lower and upper bounds on L1 of GP when this L1 is of linear order. Then I'll discuss also like this existence or absence of jumps, like can we say that in an interval there's a jump, or interval there's no jump? And finally, I'm going to talk about the sublinear lower and upper bounds. What do I mean by this? So like here in this kind of onion example, we saw that there's certain jumps that go from some polynomial to another polynomial. So we want, in order to be able to detect these jumps or to prove that such a jump exists, we need to say something not only about linear size components, but also like sublinear size components. So this is what I want to like to do. Okay, so let's define these level sets. I think Nikos was calling this WND. I call it SND. And it's just the set of vertices that have degree at least D. And our first result is the following. It says, well, I mean, look at how many of these vertices you have, and say that you have a linear amount. So then if you take P smaller than 1 over D, then your largest component cannot be larger than essentially delta n. And if you take P to be larger than 1 over D, then you can prove that you have a giant component of size at least delta n, right? So it's like, as I said, like it's an upper bound and a lower bound for the largest component on the order of linear, on the linear order, right? So let me say that A is quite easy to prove because essentially, like if your P is much more than 1 over D, then any vertex that won't be in this set will be isolated. And because it's isolated, it's clear that it cannot contribute on the largest component. So A is really like these sort of statements are the easy ones. These ones are more tricky because you have to prove now that, well, certainly you have many edges because, I mean, you had these vertices and now your probability is larger than 1 over D. So you expect that these vertices here will still have many edges going out, but you have to show that they connect. And they'll connect to form like a big component. And let me say that I'll say something about this proof and how you use switching method to do this at the end. The theorem is nice, but it only provides information at a linear scale. So as I said, like it doesn't see anything like a square root of n or n to the 2/3, which we would need to show this kind of infinitely many jumps phenomenon. So this is nice for the linear case. And it locates what we call the delta threshold. And what I mean by delta threshold, it means the moment where the proportion of vertices in the giant component surpass like this delta. So it's a moment that you contain at least a delta proportion, right? So before this 1 over D, before 1 over D, you don't contain it. Your largest component is at most of size delta n, and after this, you do. So it really allows you to do this. And for example, it allows you to control the leading constant of L1 of GP. So for example, if you want to prove our first example, which was this one, this one here, to prove that this thing holds, you can use this theorem because this theorem will allow you to draw precisely this function. It will still, in fact, it will give you something a bit better than this. Okay, so this for linear lower and upper bounds on the largest component. So, So what else can we say? So what about the jumps? So as I said, like we would like to understand when do you have a jump and when you don't have a jump. So let's start with the absence of jumps. And our result says the following. So imagine that you have, let's define this Sn D1, D2, which is just the set of vertices of degree at least D1 and less than D2, right? So D1 is more than D2. So you just take the interval where like all the vertices between D1 and D2. And imagine that this thing here is small. So this set, there should be some cardinalities here, is the size of this set is small. Then if you take P2 and P1 to be in this interval, 1 over D2 and 1 over D1, then you're not going to see any jump there. I mean, like jump in the sense of a linear jump, right? So the largest component in GP1 and the largest component in GP2 are going to have roughly the same size, or like the difference, it will be sublinear. So somehow this is saying, well, if in this interval we don't have many vertices, then it's not that some magic can appear and then suddenly you will have many, like your largest component would have like a linear increase. Something like this cannot happen. So it tells you the absence of this linear increase in a very wide interval, which is essentially contained in this 1 over D2 and 1 over D1. So this is for the absence of jumps. What about the existence of jumps? When can we say that some jump appears somehow? But the more than a jump, maybe that the component changes in its size. So again, we have some hypotheses. So say that we have delta n vertices in this interval, and say that you have at least gamma n vertices of degree at least d2. Then we have two results, and these two results are a bit like depending on whether d1 and d2 are very similar or not. So if d1 and d2 are, say, a constant apart, so they converge to some constant that is larger than 1, then what you can show is that the largest component in P2 compared to the largest component in GP1 will have a linear difference. So there will be, I mean, it's not really telling you that there's going to be a jump, because maybe it could grow continuously, right? But it tells you that it changes. So if you have some situation like this, then you know that this C here, I didn't say it anywhere, but this C is strictly positive. So, I mean, you know that you get a bit more of the total number of vertices. So like your giant component grows from here to here. So in this case, like your P1 and your P2 are comparable, because this P1 divided by P2 is just 1 over d. So they are comparable, but they're not too close. So if you want them to be really like 1 plus epsilon and 1 minus epsilon, what you can do is the following. So like, yeah, take D2 and D1 to converge to 1. So they are asymptotically equivalent. And then let's say that they are equivalent to D. And then what you can say is you can take P1 to be 1 plus epsilon D over D, and P2 to be 1 minus epsilon over D. And then what you can show is that you also have this linear increase between P1 and P2. So here it's like really like a kind of sharp threshold, right? Because we are only increasing by epsilon, like we're just considering 1 minus epsilon over d and 1 plus epsilon over d, but we really see like a linear increase in the giant component. So these are two results that are somehow, there's neither that is stronger than the other one. It's just depending on where you want to put the focus. If you want a very narrow interval, then you're forced your d's to be very close. But so this thing is stronger condition, right? This is the stronger condition. But if you're happy with some piece that differ in a constant fraction, then you can have also, like, your degrees could be also more general. So as I was saying, like A gives you sufficient conditions for a linear increase in a wide interval, while B is the same, but in a narrow interval. And also, like, it's interesting because somehow it's natural that you need many things here in the middle, because the things here in the middle is the things that maybe in D1 you're not going to get it. Sorry, in 1 over D2 you're not going to get it, but in 1 over D1 maybe you're going to get it. So it makes sense that these things have to be large, but also this condition here is also necessary, so it cannot be drawn. So we sort of need this condition, because otherwise we have counterexamples. Okay, so let me just talk about the last thing, which is this sublinear bounds. So remember that we had this phenomenon of this graph we call the onion, where you had like these jumps, and these jumps were at a scale that was not linear, but it was really like sublinear. So we were going from a polynomial n to the something to n to the something else. So we need some sort of tools to kind of detect this phenomenon. So we have two results essentially. The first one says that the largest component cannot be larger. So now here S and D can be anything that goes to infinity. So it could go to infinity as a log n, or as a square root of n, or as n to the 2/3. It doesn't have to be linear. And what we prove is that in fact, like, your largest component cannot be larger than this plus an extra amount. And then I'll say something about this extra amount. And then on the other direction, if it turns out that in S and D, the number of edges that you see, that you span from S and D, is much larger than the number of edges that you span from the vertices that they are in the complement of S and D, then you can show that there is a component that contains almost all the edges. And almost all the edges sometimes is also almost all the vertices that matter, which are the ones in S and D. So somehow this thing is a negative result. It says that L1 cannot be very large. And this thing here is showing the existence of a large component. So it's telling you that L1 is not too small. Okay, so this thing allows us to prove upper and lower bounds that are sublinear, which is the interesting thing. And just let me say, yeah, like this expression here, if you look at this expression, 1 minus p to the dv, 1 minus p to the dv is just the probability that all the edges around dv failed to percolate. So this is the probability that at least one edge percolated. So this is the probability that B is not isolated in GP. So this it's related. So let me finish with a bit of ideas of how do we prove these things. And as I was saying, like what I would like to talk about is the switching method. So the switching method is a technique that was introduced by Brandon McKay in the 1980s. And the main idea is the following. So imagine that you have, so this is the set of graphs that we are thinking about, and we are just taking one of these elements uniformly at random. So imagine that you have two sets, A1 and A2. And these are just subsets of, this should be graph with a given degree sequence, not the regular. And our goal is for, say, for a given subset like A1, we want to estimate the probability of this, right? For example, A1 could be all the ones that have a component of size, blah, blah, blah. And this is just because we are in the uniform distribution, this is just the how many do you have that satisfies it divided by the total. And this is what we're going to exploit. So what we're going to do, so what's this idea of switching method is we're gonna kind of define some operations over the graph that will transform the graph. So this SI, these are the switches. So the switches will be a collection of operations that, given some of the elements, maybe not all the ones, but given some of the elements in A1, will transform them into another graph in GND. So they will preserve the DD sequence, but probably they will not preserve the property A1. Okay, so you have this collection of operations, and then what you do is you set a bipartite auxiliary graph, where on one hand you have all the graph in A1, and on the other side you have all the graphs in A2. And then you put an edge between two graphs, G and G prime, G in A1 and G prime in A2. If there exists a switching that turns this graph here, G, into this graph S of G. Right? So like for any pair of graphs that there's an operation that transforms one into the other, you just put an edge there. And switching is just double counting these edges. So you just double count the number of edges and you say, well, the number of edges here is going to be the number of elements that I have here. I have this probability here, but I could maybe just write the size of A1. So the size of A1 times the minimum degree that I will have, that this graph will have towards the other set. I will be at most the number of things that I have in A2 times the maximum degree towards the other set. So the number of edges here in the middle are bounded by these two things, and then you can just drop this thing in the middle and just bound this thing in terms of the other. So the probability of A1 is going to be at most these two quantities times the probability of A2. So sometimes the probability of A2, it's enough to say that it is 1, something like this. And if you just bound this by 1, then this will give you a bound on the probability of A1. Okay, so let me put you like a simple example. And then I'll put some example more related to the components of a graph. Let's say that we want to estimate something very simple. So we're taking a graph at random. I want to understand what's the probability that certain pair of vertices form an edge in my graph. So UV is an edge in my graph. That's what we want to give, right? And we're going to use the switching method. So how are we going to do it? We're going to say, okay, so my set A1, this is the one with the probability I want to estimate, is going to be all the graphs that have UV, an edge of my graph. And A2 is going to be the complement. Okay, so if I do the switching method, I will estimate the probability. I will bound the probability of this. So I will bound this probability here. And now it's the moment to set what is the switching. So what we're going to say is like a switching will have this UV and this CD. The UV are going to be fixed because I have fixed these two vertices. So I'm going to be choosing CD. So for each CD that is different than UV, what I'm going to do, a switch, what it's going to do is like, it's going to remove the edges UV and CD from your graph, and it's going to add the edges UC and VD in your graph. So for this reason, I need to do the switching over the set of graph that do have these edges and don't have these edges. Right? So it's better to first understand what's the operation, right? And then understand what's somehow the subset in which I can apply this operation. So let me give you a drawing. So say, for example, that CD is this thing here. So then this graph is in here. Why? Because I have the edge UV and I also have the edge CD, but I don't have UC and I don't have also VD. So after applying the operation, I obtain this graph here. So I'm just switching these two edges, right? I'm switching these two edges by these two edges here. What's the nice thing about this is that I'm not changing the degree distribution. By doing this, the degrees are still the same, right? The degrees here were 2 and still 2. The degrees here, they were 3 and they are still 3. So I'm staying inside the set of graphs with a given degree sequence. Imagine now that I would like to switch this UV with this CD. So now G is not in BUVCD because VD, this one here, so this one here, is an edge in my graph, so it doesn't satisfy this condition. And I'm not going to do this sort of switching because if I would do this switching, then I wouldn't have like a simple graph anymore. I would have a multi-graph. So this is something that I don't. Okay, so this is the idea. And then now it's just a matter of counting. In how many ways can I go from a graph that has an edge UV to a graph that doesn't have an edge UV and vice versa? So imagine that I have a graph. AC it doesn't have the edge UV. Imagine that I don't have the edge UV. So then in how many ways can I do a switch that will have the edge UV? So I'll try to draw here. Let me try it. So I have here my, so here I have, just a second. Let me start again. So this is U and this is V, and I know that I don't have this edge, right? But I want to switch with some edge in order to have this edge. So if I want to have this edge, certainly I need to choose an edge that is here and an edge that is here. And then if I'm lucky and I don't have this edge, then I will be able to switch and obtain the edge UV. So at most, how many options I have? Well, I have DU here and I have DV here, and I can combine maybe any of these with any of these. So the total number of things that I can do is at most DU times DV. This is an upper bound on the number of switchings that can go from something that doesn't have the edge UV to something that have the edge UV. Let's go now in the opposite direction. So now I have something that has the edge UV, and I want to switch it out. So how can I switch it out? I want a lower bound. So I want to make sure that I can do this switch. So I could say, well, I can take on any other edge. I have M directed edges, and then I could try to switch these things here. But if I take any edge, right, I may have this edge here, and if I have this edge here, I cannot do the switching. So what I'm going to do is the following. Let me see. So I'm going to say, okay, so I'm going to block all the edges that are close to you. I'm going to say all the edges that are a distance at most 2 from you, I'm not going to take them. I'm also not going to take all the edges that are a distance at most 2 from V. So now take any other edge here, say CD. And now because this edge CD is not a distance at most 2 from you, I know that there's no edge here. And I know that there's no edge here. So I'm sure I can do the switching, right? And so I can choose M edges, but now I have disregarded all these ones that are at most delta square, and at most these ones that are at most delta square. Delta here is the maximum degree of my degree sequence. So I have to disregard these ones here. So the number of things that I have is at least this. Hopefully it's more or less clear what I'm doing here. So once I have all these ingredients, I can come here. I mean, this used to be like, right? I had this thing here. So I can apply this. And so I put my ingredients. I have DUDV. I have M minus 2 delta squared. And then this gives me an upper bound on the probability that I have this edge UV. And if delta squared is not too big with respect to M, then this lower bound, this upper bound, sorry, is close to the truth. Well, I mean, something like this, which is what would you expect, and also what you get if you do the configuration model. So at the end, as you see, there's some sort of double counting argument where you have to count in how many ways can you switch in one direction or the other. So let's try to explain how you can use this switching method to bound the largest component. So we'll try to prove a weaker version of our theorem, of one of the first theorems, which says something like, say that you percolate with a probability that is much larger than 1 over d, and also say that you had like linearly many vertices of degree at least d. Then you will have like your largest component should have size, say, at least delta half times m. I want to prove this, and I want to prove it with the switching method. So what I'm going to do is, first of all, I mean, the switching method is just a counting argument, but now we have GP. So GP is not really, we're not counting anything with GP, right? And different percolated graph will have different probabilities to appear. So one good option is just to think about GP as being just a red-blue edge coloring of G, meaning that like the ones I want to percolate, I put it in blue, and the ones I don't want to percolate, I put it in red. So now I have a two coloring of G. And now I'm going to condition on the number of edges that I have. So say that there's L edges that survived in GP. So I did the percolation. At the beginning, I had like M half edges, right? So I did the percolation, there's L surviving. And now if you fix the number of edges, then it is true that you have a uniform space. And each instance in this uniform space, which instance is just a graph together with a two coloring, which tells you which edges are you keeping and which ones you are not keeping. Then each ones appear with certain probability. So, and this allows you to use switchings. So we're going to be able to do switchings. So we're going to be using switchings, and we will only switch blue edges. So we're going to forget about the red edges and only switch blue edges. So what are going to be my events? My events I'm going to define my events as the following. So for every k, I'm going to define fk to be the event that GP has k components, and fk prime to be the event that GP has k components, and also the largest component is small. So this is the sort of thing I don't want to happen, right? I want this to happen, so I want to avoid this. So I want, in some sense, my goal is to show that these probabilities are not too big. So what I'm going to do is I'm going to use the switching method, and I'm going to take A1 to be this f prime of k plus 1. Here this is a bit of a trick, but this f prime, because I want to upper bound this, and A2 to be fk. So how do I prove the thing? So let me just give you first some claim that is a bit like, it's a graph theoretical claim, which is like if you have any graph, then there's at most n edges where you can cut your graph. So even if you have a lot of edges, not every edge can be a cut. So there's at most n edges that can be a cut. And also, like if you're looking for two edge cuts, a two edge cut is just two edges that when you remove them, you will cut your graph. Then you have at most n squared. So we're going to be using this. So, okay, so let's say we want to see how many operations do I have, how many switches do I have, such that if I have a graph in this f prime k plus 1, which is k plus 1 components, and they are all small, then I can switch to something that is in fk, which is something that has k components. So because we want to go from k plus 1 to k, it suffices to merge two components. Two of these k plus 1 components, I'm going to merge them into a single one, so I'll have k components. So how can I merge two components? Well, if I take two edges from different components, I have to be a bit careful, because say that I take this edge here and this edge here, and I want to switch them to join these components. Maybe if I do this operation, because now I don't have this edge here in the middle, right? This edge here in the middle, I'm not going to have it anymore. Just a second. So after the switch, this will look like this. But then maybe it could be the case that when I did this, I also split these components into two. So I don't want these sort of things to happen. So the way to avoid this is to make sure that your first component, like say your first edge that you take, say this one here, is not a cut edge, is a non-cut edge. So meaning that this edge here is not going to cut your component. And when you switch with any other edge, then you'll have a single component because this edge was not a cut edge. So how many non-cut edges do we have? Remember that there were at most n cut edges. So we have L, which is the number of edges, minus n that are non-cut. And also we need to choose like an edge in another component. And because your components are small, you have plenty of edges on the other components, because you assume that your component was small. So there's a lot of vertices outside, and these vertices outside, they have edges. So you have a lot of edges still. So there's many ways to kind of merge two components. Second part is we want to show that there's not many ways to split a component. So to go from fk to fk plus 1 prime, we need to split a component. And then in order to split a component, switching edges, we have to choose either a two-edge cut. So two edges that when we remove them, we're going to cut, or two edges that are cuts itself. So you have at most 2n squared. And then you can put everything together. There's a small claim just saying that usually L, which is the number of edges in the percolated graph, is going to be super linear. So you're going to have much more than delta n edges. And then we just put everything together. So the probability of this is at most this thing divided by the number of choices that I get here, which is something like this, times the probability of fk. And now I have here an n square, I have here n, but L was something that was growing super linearly. So this thing, all this thing here goes to 0. And the probability of this thing is little o of the probability of fk. And now we are done because we just put like everything together. So the probability that the largest component is at most something like this. It's just the probability of the union of these events, the f primes. But this is the same as the sum because these are disjoint events. And we know that each of these guys is little o of pfk. But this thing here, this sum here is just 1. So this is little o of 1. So we just proved that the probability of having a small component goes to 0 when n goes to infinity. And this is what we wanted to show. Okay. So just as a conclusion, as I was saying, like we have this percolation phenomena, which in the case of the sparse random graph with given degree sequence was very similar to the Erdos-Renyi model, but in this dense setting is quite different, it's qualitatively different. There's things coming up. It's not only about the methods that we use to prove, but really of certain phenomena that we don't see in the sparse case. And as I said, like we saw examples of sequences that had these jumps either on the constant or jumps or polynomial jumps even. So there's these very strange things going on. And we gave a number of results that can be applied in some of the situations, maybe not all the situations. And as I said, like there's still like things to understand and yeah. And we're still excited to continue this project and to, at some point, be able to give like a full description of everything. So that's everything. Many thanks for your attention.
All right. Thanks a lot, Guillem. All right.